embryological homologs. And the concept of embryological homologs is pretty simple. And I'm just going to give you a few practical connections that'll help you use this information. But the actual description of it's pretty basic. So if you look in your packets, if anybody has them, that one, the embryological homologs is essentially parts of the brain or parts of the nervous system that had developed together and maintain functional connections. Okay, so the way you can figure this out is pretty much if anybody's been through embryology, which I believe you get in, is it third quarter? Second quarter. So when you start embryology, this actually makes it really interesting because when you're first learning about neural tube and neural crest cells and telencephalon and rhombencephalon, it's all kind of boring. But when you look at it functionally, it is super interesting. So I just want to give you a basic rundown of kind of how the cortex and the cerebellum and stuff develop. So when you first start out, you have a prosencephalon, a mesencephalon, and a rhombencephalon. The first thing you might notice if you've been to club at all is that at the very beginning you have a mesencephalon. So the mesencephalon is kind of your very primitive, been there forever sort of part of the brain. So the mesencephalon starts out as a mesencephalon and it ends as a mesencephalon. Okay, and another point to kind of know about it is they start out as undifferentiated cells. So most of them they start out and they're going to either produce norepinephrine cells or their serotonin cells or they're going to be axons or whatever. Whereas the mesencephalon kind of starts out undifferentiated and stays that way as it's developing and then turns into things like your substantia nigra or your red nucleus or your corpora quadrigemina. So the mesencephalon all kind of fires together as a homolog, which is different from most of the other parts of the brain. So it's just something to think about. Now the prosencephalon is kind of the top part of the brain, and that's going to differentiate into your telencephalon and your diencephalon. Now you can kind of think of this whole diagram just the way it is, top to bottom. So your telencephalon is going to become what we know as the cortex, right? So that's going to be your thinking part of the brain. Then your diencephalon is what becomes your thalamus, hypothalamus, and all the other thalami that you'll hear about. And then the mesencephalon we already talked about, stays mesencephalon. The metencephalon, that's what turns into the pons, so this lower part of the brainstem, and the cerebellum. Now you know from the way the pons is set up, it's got those huge cerebellar peduncles coming in, so there's a ton of information going to and from the cerebellum from the pons. So those develop together, and then you have your myelencephalon, which becomes your medulla and your spinal cord, right? So that's kind of like the giant overall picture of how your brain starts developing. And the reason this becomes important is, so say your prosencephalon, right? It starts out as one thing. As it differentiates, now you have your, say, your cortex and let's just say your thalamus, right? Well, now there are two different structures in two different areas, but because they maintain this homologous connection, they actually have a lot of ability to fire together. So it's one of the reasons, this one's hard to differentiate though, because your thalamus and your cortex we almost think is the same thing, because it's hard to fire the thalamus or the cortex without firing each other, because the thalamus is kind of like your gatekeeper, right? So all the information that's coming up, I mean, your brain or your thalamus is getting screamed at like 24/7. Like mechanoreceptors are saying this, nociceptors are saying that, joint mechanoreceptors are saying another thing, and the thalamus is kind of thinking, okay, out of all that information, what's important? Let's send that to the cortex. Okay, so it's almost impossible to fire the cortex without going through the thalamus first, right? So those two are homologous pair. Another one that I want to talk about is the dorsal root ganglion. So is anybody familiar with the dorsal root ganglion? You guys, first quarter, kind of know what's going on, right? So that's what takes in a lot of your proprioception, muscle spindle responses, mechanoreceptors, that sort of thing. And that whole column is homologous. So those things are going to fire together. So when you have like an adjustment, that's one of the reasons that you don't just have a localized effect. So like you can adjust the upper neck and now your low back doesn't hurt, or your low back and now your neck doesn't hurt, or vice versa. So that's one of the reasons. Obviously, we talk about the cerebellar input, the mesencephalic input, the cortical input. So it all plays a part in it, but the fact is when you're affecting one of those dorsal root ganglia, you're also affecting the rest of them. And think of it kind of like throwing a pebble into a pond. So like if I adjust, say T6, the most input and the most firing of the dorsal root ganglion is going to be at T6. But the ones that are above and below it are going to get a little bit less and a little bit less as you go up and down the spinal column. Does that make sense? So you just think of it like that when you're firing these different areas. Is yes, technically you're probably going to have input of almost everything when you're making these adjustments, but you're looking for what's firing the most and what's causing the greatest amount of input. So another good one to recognize as an embryological homolog is the sympathetic ganglion, and that's post-sympathetic, post-synaptic sympathetics. So things that are controlling like your blood pressure, right? So they all have to fire together, because would it make sense that say you're exercising really hard and you need to start shunting blood to the muscles? It wouldn't make a whole lot of sense if you just started shunting blood to like one muscle, or just on one side or the other. So obviously these are the kind of things that have to fire together, and that's kind of why they remain connected throughout development. Is not just because we started together, we're going to fire together. It's because they have a functional purpose. So dorsal root ganglion, sympathetic chain ganglion. Another one that I think is interesting, and this is one of the ones that I'm not sure why they stay connected, but cranial nerves 3, 4, 6, and 12. So what are 3, 4, and 6? What are the cranial nerves? So what's 3? Oculomotor. 4 is trochlear. And then 6 is
abducens.
Right. So they're all the eye movers, right? So 3, 4, and 6, it makes sense that they would fire together, right? Because they're all connected to moving the eye. But their embryological homolog is also cranial nerve 12, which is, everybody know what cranial nerve 12 is? Hypoglossal, right? So tongue movements, which is kind of funny. But, you ever see somebody that's like concentrating really, really hard, and they like stick their tongue out to the side, and you're just like, why are they doing something like that? It actually has a neurological impact, because if they're firing that hypoglossal nucleus, that can also fire homologs, which can excite different areas that are trying to create cognition. So it's funny stuff. Once you start learning about all this, you start looking at people and the weird things they do, and you're like, it might actually have a purpose. Like maybe there's a lesion there. Like why are they sticking their tongue out? Maybe we need to evaluate that a little farther. We talked about the mesencephalon. The big areas of the mesencephalon we'll talk about as we get further and further into the program are the substantia nigra, the red nucleus, the oculomotor nerve, and the Edinger-Westphal nucleus. So if you can kind of just start thinking about those four, because there's a bunch of things in the mesencephalon, but those are big ones that we'll talk about a lot. The prosencephalon we already talked about, the cortex and the thalamus. Oh, another interesting one is the hippocampus and the parahippocampus. So does anybody know what lobe of the brain the hippocampus is in? What's that? It's in the temporal lobe. So actually, just real quick, because we haven't really gone over this with the intro. Is everybody clear on what the different lobes of the brain are and what the difference is between like the cortex, cerebellum, brainstem, and the different parts of the brainstem? No? Kind of? A little bit? Okay, just a real quick overview.
We're doing lobes of the brain week 10.
In advanced course.
Yeah.
I was just going to give a real basic.
Okay.
We're not going to get into what all they do, but just a real quick, this is kind of the overview of the anatomy of the central nervous system. Because you have your big brain here, right? Kind of a brain-ish. And then you have your cerebellum back here, and then you have this. Okay, so we're gonna, actually this week is the week that we're doing the brain dissection. So if any of you haven't seen a brain dissection yet, definitely come. It's gonna be on Wednesday at noon. We're gonna do it in the dissection lab, and we're gonna be going over kind of all this stuff in a lot more detail, but you're actually gonna get to see it, which is awesome. Because you'll learn this stuff in class, and you'll say, oh, here's the spinal cord, and it looks like this big, and then you actually dissect it, and you realize it's about that big, and this stuff really starts to take hold. But basically you have a couple different, you have 4 main lobes in your cortex, and your cortex is the most advanced part of your brain. And as you think about the cortex in general, just think of, as it moves farther forward, that's the newer and more cognitive aspect. So when you get farther and farther towards the front, this is the areas that make you more human, that make your decisions make you kind of who you are. So you have a sulcus that runs down here, and it's going to separate your frontal lobe from your parietal lobe. And then you also, down here you're going to have a lobe, and here you're going to have a lobe. So you have a temporal lobe and an occipital. So if I was to just give very, very generalization about these lobes, this is motor control and cognition, so the things we think about. Parietal is going to be more sensory, so the input that you get from your body, things that are going on in your environment. The temporal lobe has a lot to do with hearing, but also with memory. And then occipital is going to be mainly just with eyesight. So it does other stuff, but most of your eyesight is going to be occipital. And then in your brainstem here, this is where your mesencephalon sits. Then right below it, you have your pons. Then you have your medulla. And then the medulla kind of tapers off into your spinal cord. And then back here, you have something called the cerebellum. And the cerebellum has a lot of connection with the frontal lobe here, because the cerebellum is a highly, highly concentrated mass of neurons. And it's going to talk to the frontal lobe and say, okay, I want to move my right arm. And it's going to coordinate with the cerebellum, and the cerebellum is going to say, okay, here's where your right arm is right now. This is where it moved to. Is that right? Do we need to change anything? So this is kind of like the checks and balances for when you're doing motor control. So this is just a very general overview of how the brain's set up. Like I said, during the dissection, we're going to go into different parts of these different lobes, what they control. And the reason I brought this up is the temporal lobe has this structure called the hippocampus and the parahippocampus, which when it starts off isn't folded at all, and as it starts to develop, it kind of infolds in itself. And so hippocampus doesn't stay in just one area. It's kind of, as it folds, it goes into different physical areas, but it maintains the total same functional structure. And this has a lot to do with memory. So it allows you to integrate different memories and have different connections coming to the hippocampus, even though it's not just in one kind of central area there. So, but the hippocampus is in the temporal lobe there. All right, so so the big deal about embryological homologs in general is when you get an idea of what fires together, you can use that for rehab, right? So that's really what we're getting at with all these kind of lectures and stuff is, this is really a general overview. Like I said, Mondays are just to, get you kind of thinking about this stuff, because we could go into a lot more detail with everything. But, I mean, just think about the fact that, the dorsal root ganglia fires together. So if you can't, so say somebody's in like super, super acute pain and like their low back, but, you're not able to adjust them because you can't get them in the side posture, you can't do anything, but you're going around and you find that there's subluxation somewhere else, adjusting them in those other areas is helping, not only because of, the fact that you're fixing subluxation, but you're also activating that dorsal root ganglia that's going to help gate the pain in those areas that they're really having this acute pain in. So maybe the first time you come in, you can only adjust their neck when their low back hurts. Or, vice versa. Maybe their low back hurts and they're subluxated, or their neck hurts, and you can't touch their neck, but you can adjust their thoracic. So chiropractically, that's kind of a really easy way to see how this stuff works. Now, more neurologically, we like to think about this with like the mesencephalon and eye movements, and you'll learn later how the eye movements are really highly coordinated with the cortex. So the frontal lobe and the parietal lobe have a lot to do with eye movements. And if you have somebody that's isn't able to get adjusted because you're doing your evaluation, they're just they're fried, you can start using eye movements to rehab say the frontal lobe, so that area will be able to kind of gate pain and work on allowing them to receive the adjustment in subsequent treatments. So when you come to the advanced ones, we get into that a little bit heavier. Like Josh said, we're going to do lobes of the brain, where we'll basically take each one of these lobes and break them down into, what are the different areas of this lobe, what does each area do, how do you test it, and then how do you treat it, and how do you retest it, which is really important. So I kind of wanted to give it, since we have a lot more younger people than we do normally, I kind of wanted to open up the last couple minutes for questions, and any challenges you guys have been having so far with, have you been able to use this in class? Have you been able to work on people at all? Any questions about what we've talked about in the last couple weeks?